a WikiVidi documentaries production. Don't forget to like and subscribe. Enjoy. Mars. Synodic_period 779.96 d, average_speed 24.007 km per second, mean_anomaly, inclination, ASC_node, arc_Piri, satellites 2, all satellites yes, physical_characteristics yes, mean_radius, 3389.5 plus minus, equatorial_radius 3396.2 plus minus, polar_radius 3376.2 plus minus, flattening, surface_area 144,798,500 square kilometers, volume, mass, density 3.9335 grams/cm3, surface_graph 3.711 meters/s2, moment_of_inertia_factor, escape_velocity 5.027 kilometers per second, sidereal_day, rot_velocity 868.22 kilometers per hour, axial_tilt to its orbital plane, right_ASC_north_pole, declination, albedo, temp_name 1 Kelvin, min_temp_1, 130 K, mean_temp_1 210 K, max_temp_1 308 K, temp_name 2 Celsius, min_temp_2 minus 143 degrees Celsius, mean_temp_2 minus 63 degrees Celsius, max_temp_2 35 degrees Celsius, temp_name 3 Fahrenheit, min_temp_3 minus 226 degrees Fahrenheit, mean_temp_3 minus 82 degrees Fahrenheit, max_temp_3 95 degrees Fahrenheit, magnitude, angular_size 3.5 25.1 inches, atmosphere_F, surface_pressure 0.636 kPa 636 kilopascals, atmosphere_composition. Mars is the fourth planet from the Sun, and the second smallest planet in the solar system after Mercury. In English, Mars carries a name of the Roman god of war, and is often referred to as the Red Planet, because the reddish iron oxide prevalent on its surface gives it a reddish appearance that is distinctive among the astronomical bodies visible to the naked eye. Mars is a terrestrial planet with a thin atmosphere, having surface features reminiscent both of the impact craters of the Moon and the valleys, deserts, and polar ice caps of Earth. The rotational period and seasonal cycles of Mars are likewise similar to those of Earth, as is the tilt that produces the seasons. Mars is the site of Olympus Mons, the largest volcano, and second highest known mountain in the solar system, and of Valles Marineris, one of the largest canyons in the solar system. The smooth Borealis Basin in the northern hemisphere covers 40% of the planet and may be a giant impact feature. Mars has two moons, Phobos and Deimos, which are small and irregularly shaped. These may be captured asteroids, similar to 5261 Eureka, a Mars Trojan. There are ongoing investigations assessing the past habitability potential of Mars, as well as the possibility of extant life. Future astrobiology missions are planned, including the Mars 2020 and ExoMars rovers. Liquid water cannot exist on the surface of Mars due to low atmospheric pressure, which is less than 1% of the Earth's, except at the lowest elevations for short periods. The two polar ice caps appear to be made largely of water. The volume of water ice in the South Polar Ice Cap, if melted, would be sufficient to cover the entire planetary surface to a depth of 11 meters. In November 2016, NASA reported finding a large amount of underground ice in the Utopia Planitia region of Mars. The volume of water detected has been estimated to be equivalent to the volume of water in Lake Superior. Mars can easily be seen from Earth with the naked eye, as can its reddish coloring. Its apparent magnitude reaches -2.91, which is surpassed only by Jupiter, Venus, the Moon, and the Sun. Optical ground-based telescopes are typically limited to resolving features about 300 kilometers across when Earth and Mars are closest, because of Earth's atmosphere. Physical characteristics. Mars is approximately half the diameter of Earth with a surface area only slightly less than the total area of Earth's dry land. Mars is less dense than Earth, having about 15% of Earth's volume and 11% of Earth's mass, resulting in about 38% of Earth's surface gravity. The red-orange appearance of the Martian surface is caused by iron oxide, or rust. It can look like butterscotch. Other common surface colors include golden, brown, tan, and greenish, depending on the minerals present. Internal structure. Like Earth, Mars has differentiated into a dense metallic core overlaid by less dense materials. Current models of its interior imply a core with a radius of about 1794 ±, consisting primarily of iron and nickel with about 16–17% sulfur. This iron sulfide core is thought to be twice as rich in lighter elements as Earth's. The core is surrounded by a silicate mantle that formed many of the tectonic and volcanic features on the planet, but it appears to be dormant. Besides silicon and oxygen, the most abundant elements in the Martian crust are iron, magnesium, aluminum, calcium, and potassium. The average thickness of the planet's crust is about, with a maximum thickness of, Earth's crust averages. Surface geology. Mars is a terrestrial planet that consists of minerals containing silicon and oxygen, metals, and other elements that typically make up rock. The surface of Mars is primarily composed of tholeiitic basalt, although parts are more silica-rich than typical basalt and may be similar to andesitic rocks on Earth or silica glass. Regions of low albedo suggest concentrations of plagioclase feldspar, with northern low albedo regions displaying higher than normal concentrations of sheet silicates and high silicon glass. Parts of the southern highlands include detectable amounts of high calcium pyroxenes. Localized concentrations of hematite and olivine have been found. Much of the surface is deeply covered by finely grained iron oxide dust. Although Mars has no evidence of a structured global magnetic field, observations show that parts of the planet's crust have been magnetized, suggesting that alternating polarity reversals of its dipole field have occurred in the past. This paleomagnetism of magnetically susceptible minerals is similar to the alternating bands found on Earth's ocean floors. One theory, published in 1999 and re-examined in October 2005, is that these bands suggest plate tectonic activity on Mars 4 billion years ago, before the planetary dynamo ceased to function and the planet's magnetic field faded. It is thought that, during the Solar System's formation, Mars was created as the result of a stochastic process of runaway accretion of material from the protoplanetary disk that orbited the Sun. Mars has many distinctive chemical features caused by its position in the Solar System. Elements with comparatively low boiling points, such as chlorine, phosphorus, and sulfur, are much more common on Mars than Earth. These elements were probably pushed outward by the young Sun's energetic solar wind. After the formation of the planets, all were subjected to the so-called late heavy bombardment. About 60% of the surface of Mars shows a record of impacts from that era, whereas much of the remaining surface is probably underlain by immense impact basins caused by those events. There is evidence of an enormous impact basin in the northern hemisphere of Mars, spanning 10,600 by, or roughly 4 times the size of the Moon's South Pole Aitken Basin, the largest impact basin yet discovered. This theory suggests that Mars was struck by a Pluto-sized body about 4 billion years ago. The event, thought to be the cause of the Martian hemispheric dichotomy, created the smooth Borealis basin that covers 40% of the planet. The geological history of Mars can be split into many periods, but the following are the 3 primary periods. Geological activity is still taking place on Mars. The Athabasca Vallis is home to sheet-like lava flows created about 200 Mya. Water flows in the grabens called the Cerberus Fossae occurred less than 20 Mya, indicating equally recent volcanic intrusions. On February 19, 2008, images from the Mars Reconnaissance Orbiter showed evidence of an avalanche from a 700 meters cliff. Soil. The Phoenix Lander returned data showing Martian soil to be slightly alkaline and containing elements such as magnesium, sodium, potassium, and chlorine. These nutrients are found in soils on Earth, and they are necessary for growth of plants. Experiments performed by the lander showed that the Martian soil has a basic pH of 7.7 and contains 0.6% of the salt perchlorate. Streaks are common across Mars, and new ones appear frequently on steep slopes of craters, troughs, and valleys. The streaks are dark at first and get lighter with age. The streaks can start in a tiny area, then spread out for hundreds of meters. They have been seen to follow the edges of boulders and other obstacles in their path. The commonly accepted theories include that they are dark underlying layers of soil revealed after avalanches of bright dust or dust devils. Several other explanations have been put forward, including those that involve water or even the growth of organisms. Hydrology. Liquid water cannot exist on the surface of Mars due to low atmospheric pressure, which is less than 1% that of Earth's, except at the lowest elevations for short periods. The two polar ice caps appear to be made largely of water. The volume of water ice in the south polar ice cap, if melted, would be sufficient to cover the entire planetary surface to a depth of 11 meters. A permafrost mantle stretches from the pole to latitudes of about 60 degrees. Large quantities of water ice are thought to be trapped within the thick cryosphere of Mars. Radar data from Mars Express and the Mars Reconnaissance Orbiter show large quantities of water ice at both poles and at middle latitudes. The Phoenix lander directly sampled water ice in shallow Martian soil on July 31, 2008. Landforms visible on Mars strongly suggest that liquid water has existed on the planet's surface. Huge linear swathes of scoured ground, known as outflow channels, cut across the surface in about 25 places. These are thought to be a record of erosion caused by the catastrophic release of water from subsurface aquifers, though some of these structures have been hypothesized to result from the action of glaciers or lava. One of the larger examples, Mare Diem Vallis, is 700 kilometers long, much greater than the Grand Canyon, with a width of 20 kilometers and a depth of 2 kilometers in places. It is thought to have been carved by flowing water early in Mars history. The youngest of these channels are thought to have formed as recently as only a few million years ago. Elsewhere, particularly on the oldest areas of the Martian surface, finer scale, dendritic networks of valleys are spread across significant proportions of the landscape. Features of these valleys and their distribution strongly imply that they were carved by runoff resulting from precipitation in early Mars history. Subsurface water flow and groundwater sapping may play important subsidiary roles in some networks, but precipitation was probably the root cause of the incision in almost all cases. Along crater and canyon walls, there are thousands of features that appear similar to terrestrial gullies. The gullies tend to be in the highlands of the southern hemisphere and to face the equator, all up poleward of 30 degrees latitude. A number of authors have suggested that their formation process involves liquid water, probably from melting ice, although others have argued for formation mechanisms involving carbon dioxide frost or the movement of dry dust. No partially degraded gullies have formed by weathering and no superimposed impact craters have been observed, indicating that these are young features, possibly still active. Other geological features, such as deltas and alluvial fans preserved in craters, are further evidence for warmer, wetter conditions at an interval or intervals in earlier Mars history. Such conditions necessarily require the widespread presence of crater lakes across a large proportion of the surface, for which there is independent mineralogical, sedimentological and geomorphological evidence. Further evidence that liquid water once existed on the surface of Mars comes from the detection of specific minerals such as hematite and goethite, both of which sometimes form in the presence of water. In 2004, Opportunity detected the mineral jarosite. This forms only in the presence of acidic water, which demonstrates that water once existed on Mars. More recent evidence for liquid water comes from the finding of the mineral gypsum on the surface by NASA's Mars rover Opportunity in December 2011. It is believed that the amount of water in the upper mantle of Mars, represented by hydroxyl ions contained within the minerals of Mars geology, is equal to or greater than that of Earth at 5,300 parts per million of water, which is enough to cover the entire planet to a depth of. In 2005, radar data revealed the presence of large quantities of water ice at the poles and at mid-latitudes. The Mars rover Spirit sampled chemical compounds containing water molecules in March 2007. The Phoenix lander directly sampled water ice in shallow Martian soil on July 31, 2008. On March 18, 2013, NASA reported evidence from instruments on the Curiosity rover of mineral hydration, likely hydrated calcium sulfate, in several rock samples including the broken fragments of Tintina rock and Sutton-Inlier rock, as well as in veins and nodules in other rocks like Knorr rock and Wernick rock. Analysis using the rover's DAN instrument provided evidence of subsurface water, amounting to as much as 4% water content, down to a depth of 60 centimeters, during the rover's traverse from the Bradbury landing site to the Yellowknife Bay area in the Glen Elg terrain. In September 2015, NASA announced that they had found conclusive evidence of hydrated brine flows on recurring slope lineae, based on spectrometer readings of the darkened areas of slopes. These observations provided confirmation of earlier hypotheses based on timing of formation and their rate of growth, that these dark streaks resulted from water flowing in the very shallow subsurface. The streaks contain hydrated salts, perchlorates, which have water molecules in their crystal structure. The streaks flow downhill in Martian summer, when the temperature is above -23 degrees Celsius, and freeze at lower temperatures. On September 28, 2015, NASA announced the presence of briny flowing salt water on the Martian surface. Researchers believe that much of the lower northern plains of the planet were covered with an ocean hundreds of meters deep, though this remains controversial. In March 2015, scientists stated that such an ocean might have been the size of Earth's Arctic Ocean. This finding was derived from the ratio of water to deuterium in the modern Martian atmosphere compared to that ratio on Earth. The amount of Martian deuterium is 8 times the amount that exists on Earth, suggesting that ancient Mars had significantly higher levels of water. Results from the Curiosity rover had previously found a high ratio of deuterium in Gale crater, though not significantly high enough to suggest the former presence of an ocean. Other scientists caution that these results have not been confirmed, and point out that Martian climate models have not yet shown that the planet was warm enough in the past to support bodies of liquid water. Brought to you by WikiVidi documentaries. Would you like to know more?